Hello and welcome to C++ Weekly. I'm your host, Jason Turner. In this episode, I am going to try to dive a little bit into constexpr and what I think it means, the advantages and disadvantages of constexpr, as well as something of a little bit of a deep dive into the actual compiler optimizations that are possible with constexpr. So for this particular example today, I have built a standard map versus a simple constexpr map. And I'm going to not do a lot of live programming today. Instead, I'm going to be walking through what the code is actually doing. Now, at the moment, this code is set up to compile with standard map. I'm going to change this real quick to use my constexpr map. And then we're going to actually walk through this code now. So I have this extraordinarily simple constexpr capable map type that I've actually used in several places, and I've given versions of it to clients and I teach it in classes and that kind of thing. So it's just a template over a key value pair, and then since this is a constexpr thing, it has a fixed size known at compile time, and we have to provide this size, at least at the moment with the way this is currently written. This has no constructors or anything, so it's all very straightforward. So I have an array of pairs of key and value, which is not very surprising for a map. This is also would be called a dictionary lookup in other programming languages. And then the size of the array, which is this templated size t, and this is the name of the object here, it's data. Then I have a constexpr at function, and realistically, this should be no discard, and yeah, like that. So this is a simple const lookup. There's no way to add elements to this or anything at this point. And if you pass in a key, then it does a simple find if. Now you might notice, and I will just go ahead and give you a sneak peek here, that this is doing a linear search through the data. And that is actually intentional because this is actually more optimizable than if I did a binary search through this data, which might seem unbelievable, but it is true, particularly with small size sets. And given that most of the things that you're going to want to put in a constexpr case are probably going to be small things, like I'm thinking in some cases here, maybe it is a name to value conversion or a value to name conversion for an enumeration, something like that. That's really the goal of this. And this comes directly from real code that I've seen where you have lots of static const standard map kind of things versus constexpr data lookup, because people want to have this conversion to and from values to strings with their enumeration values. So I'm doing a linear search here. And then if the value does not equal end, then I return the value that was found. Otherwise, I throw a range error. Yes, it is in fact valid code to throw an exception from a function that is marked constexpr. So the key thing that you need to learn here is that constexpr does not mean that this function will be called at compile time. It simply means that it can be called at compile time in the context of creating a constant expression. That's what constexpr is. It's a portmanteau of constant expression, constexpr. So then I've got my set of values, and this is our pretend set of lookup values into some sort of enumeration or a table of color data or something like that. I have 8 values, and they are currently in alphabetical order. They were originally in numeric order. I've played with this a few times just for whatever reason. I've just been messing around with the size and order of these things. And now you might notice if you were to scroll over here and look at the compiled output that this map doesn't actually show up anywhere in the code. I need code that calls this at function, since this is a constexpr function, and I need that code to itself not be constexpr or inline, so it shows up in our compiler explorer output here. And I am taking a string view. It is intentional that I am not taking it by reference. It's generally recommended to take string view objects by value because they are simply a pointer followed by a length. And that will be key in just a moment here. And then I have my static constexpr auto. Now I know some of you would say that the static here is redundant. That is not true. If I don't have the static here, this becomes now a value that is on the stack. Now I haven't actually played with this in this particular code, but I can see it here. Okay, so this generated 144 instructions. If I put the static back, it's 148. It's actually slightly more. But what you'll notice if I take the static out is that this table of data is actually being copied into this function call stack. And this is with full optimizations O3 turned on. So I want this static constexpr map so that it is calculated exactly once at compile time and stored in the constant section of the binary. So that's what I have now. Now this lookup value takes the string view, and notice this is a pair, this is a map of string view to int. So the string view is allowed here. These are all compile time known values. These are compile time constants. A character string literal, as this technically is valid for the lifetime of the program. I can safely create a view of this and store a view of this. Now, if this was a standard string that I was doing right here and creating a string view of it, that would be very bad. That would be something that would pop off the stack that would cause undefined behavior. Trust me, all of this code as it stands is well-defined behavior. So I am given a random value here, and all I want to do is return the integer to it that it represents. So we're going to go ahead and look at this code. We're going to actually walk through this disassembly in way more detail than I tend to. And let's go ahead and give us just a little bit of zoom in here. Now, I said that we've got this value, this string view here is being passed by value intentionally because it is a pointer to the start of the data followed by a length. So now the compiler is actually going to pack this together into two different registers in our 64-bit ABI that we're using here with GCC. So what we're going to end up with here is that this string view is going to be two registers, RSI, that is the pointer to the start of the string data, and then RDI is the length of the data passed in. So this value here, we can actually see start to be referenced here is RDI and here is RSI in our compiler explorer window. So we come in, we save a couple of registers, we save R12, we save RBP, we subtract R8 from RSP, that's the current stack pointer, and then we do this, compare RDI to 5. That is saying, is the length of the string that was passed into me 5? And let's see, what values could potentially be 5 length? That is black, that is green, that is white. Now, keeping in mind we're in GCC with full optimizations turned on. It could be one of those three colors. So if it is a length of 5 string passed into us, then we jump down to L41. And that gets us to here. We are doing this comparison of RSI, D-word pointer, RSI, notice these brackets, it's actually dereferencing that. It says, I know this is a pointer, I want you to give me the value that's at this memory location. And it's comparing it to this rather odd number right here. And if it is equal to that, then it jumps down here to L45, and then it does another comparison. So let's look at what this means exactly. If I mouse over this in Compiler Explorer, I get this hexadecimal value, 63, 61, 6C, 62. Now, if you know anything about ASCII, this should look a little bit suspicious. So I'm going to pull up an ASCII chart. Let's mouse back over this. So we see 63. If we look this up in our hexadecimal ASCII chart over here, here we go. It is 63, that is equal to lowercase c. 61 is equal to A. 6c is equal to L. And 62 is equal to B. So what we get is B, L, A, C. So it has compared this. Now this, the higher order bit is on the wrong end here. But it has compared the first 4 characters of the string to see if they are B, L, A, C. So if they are, then we jump down to L45, and it compares the last byte of the incoming string, it's RSI plus 4, the 5th character of it, to the value 107, which is 6B in hex. And in fact, 6B is K. So this is the last value that we are looking for. Now it knows at this point, when we have gotten here, that it has just matched the character string black. It has the right length, it has the right first 4 characters, it has the right last character. And if it all matches up, then we load in here this lookup value into EAX and jump if not equal. So that would be in the failure case to L3, where it compares those first 4 characters now to another set of values and goes down the same whole rabbit hole here, doing another set of searches. And if it is L18, which means that we did successfully match to black, then we want to go to L18 is right here. Then when we get to L18, we are basically just returning from the function. So in the case that it was L3 and we come back up here, this would have also been the fall through case from L41. So in this case, if we had not matched the BLAC, we still would have fallen through down to here, which reading from the right this time would be GREE. So now it's trying to match against green. And if it is not equal to that, then it jumps down to L35 and it tries to match the next 5-letter word, which should be white. So I expect that 77 is W. And sure enough, 77 in ASCII is W. And it tries to match against white. And if at any point it realizes that it's reached some dead end here and it's decoding lookup table of these values, then it's going to end up in L23. This looks like it's, let's see, L23, L23. There's a few different ways for it to get to L23. And this is where it actually throws this range error. So this actually ends up being an extraordinarily fast lookup table for these potential values. Now let's take a quick aside and let's look at Clang. I'll go to Clang trunk. And now when we have this lookup value here, Clang is not doing the same thing at all. It doesn't generate this lookup table at all. In fact, it actually generates this find if loop, and this will be important later. So we're going to go back to the GCC one. That was GCC 10. Oh, I had on 10.1, 10.2. I expect it to be pretty much the same. Yes, 10.2 looks the same. And so I'm going to do a quick thing here. Just going to give myself access to the static constexpr map down in here. This is not how you would normally do this. So I can make this a constexpr value, and this should compile without any problem. And if I return this value from main, then I am just going to see what 2 is going to be returned from main. So if we get down into main here, we've got move 2 into EAX, no big deal. And that's all that main becomes. Now, of course, you're probably wondering what happens if I try to access a value that is not known. If I do just gren here, and I am assigning this to a constexpr value, I am going to get a compile time failure because I cannot throw in a constant expression during the evaluation at compile time here. But if this is no longer a constexpr value, then this all becomes valid C++ again, and this will compile. And now our main should become a call to, oh, it actually becomes a call to the at. It did not inline the throwing of the exception. That's fine. So of course, you're wondering what's the end result of all of this. Let's just do one more quick comparison. I'm going to remove this body of main. And we're going to scroll back here, and we've got 148 instructions, and we actually can, as you've seen, walk through every single one of these instructions and have an understanding as to what the code is doing. It's a lookup table of all the values here, a lookup table of the strings. It's all very nice and clean. Now, if I go with a standard map here, we basically can no longer tell what's going on at all. It does a pretty good job of not generating too much code, but a fair bit is actually generated here, 500 instructions or whatever, and constant values. But what it has to do is it must allocate for each node in the map. It has to call new, it has to do this allocation. So I did a static const map here. But we can see the calls to delete, and we should be able to see the calls to new as it's actually allocating each one of these nodes that have each of these values in here. And then we'll probably see maybe something similar for string comparisons. Calls to lookup value. So several things can't be optimized here. The compiler has to have a guard variable around this because it's a static value, and it has to make sure that it was initialized, and it has to allocate all of these nodes, and it generates more code. So I've brought this into the awesome quickbench tool, and we're going to take a quick look at that. For the sake of quickbench, I've done a couple of things here. I have these fixed table of color values that I was showing you before. I also have a randomized ordering of them, so that it's a randomized ordering that is known at compile time, but to make sure that everyone is on fair ground here, I've got a const map of these things with these color values, and then in quickbench, for each loop iteration, I'm incrementing a variable, and I'm saying, given the current value modded against the size of the random set of color names, look up one of those here. So I'm just looking this up, and then I'm calling map.at on that. So it's accessing them out of order and in a randomized way, but in a fixed randomized way. So there's not going to be any jitter or question between the different ways that we're running this. And then I've got my static constexpr version, and this is interesting here. So one of them static constexpr, the other one is just const, but they're exactly the same otherwise. And then I'm comparing it to standard map. And I've got this with GCC 10.1, C++ 20, optimization level 03. I'm going to run this benchmark. Okay, so we're going to flip over to the chart here. And it did just run this benchmark, and we can see the standard map is taken 65 whatever units of time. This is all relative time, which is 11 times slower than the constexpr map. Now keep in mind, this constexpr map's theoretically doing this linear lookup, but the flat map, so GCC said, I am unable to, for whatever reason, optimize this in the same way. Now it could have, because a const to initialize a constant expression. It could have chosen to do the same set of optimizations. It didn't. That's the choice of the compiler there. The constexpr one, though, it greatly took advantage of, and as we see, we're getting 11 times faster than this standard map. And even just basically a static const flat map here with a linear search is faster than standard map, but this change is dramatic. So when we looked at the code, we saw that Clang was not doing the same kind of optimizations that GCC was. So let's compare this against Clang 10. So we get basically the results that we would expect here because Clang isn't doing that extra level of optimization that theoretically is possible in generating this lookup table here with the constexpr data. We still get something that is considerably faster than a standard map for this small set of values. Now I will say, because I did test this, that if the set of values gets big, then the linear search starts to become a problem. Obviously, if it gets to some level that the compiler doesn't optimize, then that's where you are. But we can see that Clang makes no difference between the constexpr map and the flat map in this case, and that's just, well, the flat fixed map. I called it flat map. I probably should have called it non-constexpr fixed map, something like that. Clang is unable to make this distinction, but GCC can. So, and either way, again, this is much better for several reasons than doing a standard map, which I've already mentioned. Lower memory usage, fewer heap allocations, or no heap allocations in this case, the potential for greater compile time optimization, and well, then you're probably obviously wondering about the next question, which is compile time. How does compile time vary for these? So you'll notice here that Fred has this discover build bench. So I do suggest that you check out these tools, quickbench and buildbench, and I will have links to them in the notes for this episode. So let's see how the build time compares. So I've got here my simple standard map, and this is exactly the same deal. I am doing this lookup into a random location or whatever. In this case, I'm using argc to do that, and I'm doing this pseudo-random fixed randomized lookup. And then I am doing this, the same exact thing with my constexpr map. And I've only included the headers that were necessary, string view, algorithm, utility, and array. And I should probably add here standard except because I am throwing range error. And then this should all be technically correct. Utility for pair, array for array, algorithm for find if, string view for the string view, standard except for the range error. And for map, I am including only map and string view. So let's go ahead and analyze this build time with GCC. GCC is the one that we've already proven gives us considerably better performance. Okay, so let's look at the chart. And we can see that with GCC, the constexpr map took about twice as long, 1.7 times longer to compile than a standard map. Now, Clang didn't do the same amount of optimization as GCC did. So let's compare what Clang looks like for the same thing. I also just realized that I should have technically included pair and array in my standard map comparison here, but I don't believe that would have made any difference at all. We're going to leave it the same, and we'll compare against Clang. So with Clang, we get standard map and the constexpr map taking effectively the exact same amount of time to compile. It is, quote, 1 times slower than standard map. So you get the trade-off. You get the incredible runtime performance in the case where techniques like this make sense and work for you. Almost always a better idea than standard map, but you do have to pay a little bit of compile time overhead. Now, it would be a topic for, well, honestly, one of my classes, which once the world opens back up to that kind of thing, you are welcome to attend, where we discuss how to put some of these constexpr things perhaps behind a compilation firewall or something like that, so that it doesn't have to affect every single C++ file that uses the map, but you still get all of the benefits of having the data optimized and known at compile time. So there is my standard map versus a very simple constexpr map shootout for the kinds of things that we would want to do for compile time known data and lookup of key value pairs. I hope you enjoyed this episode of C++ Weekly. Definitely be sure to subscribe, give it a thumbs up, and share these videos with your friends.